The equations of motion in polar coordinates is exactly the same as all of the other coordinates that we've used so far. We use the univectors of the polar coordinates instead of normal and tangential or rectangular coordinates. So if we have here an origin O, a reference plane here, and our particle is up here, we draw a line from the origin to the particle. This is our position R, and then our univector here extends R, so that's our ER. Our transverse univector is 90 degrees perpendicular to that and is in the direction of increasing theta, so this would be our E theta, or our transverse direction. Now when we're looking at the forces, I'll redraw this and I'll just draw the particle here. So then we're dividing our forces, and we want to know the forces along the ER direction, so we're summing the forces in the R direction, and then we're summing the forces in the transverse direction. Then when we look at mass times acceleration, we look at the radial and transverse acceleration. So here we would have mass times acceleration radial, and here mass times acceleration transverse. We have equations for the radial and the transverse accelerations already derived from our kinematics. So here we would have summation of force transverse is equal to mass times R double dot minus R theta dot squared, and then our summation of forces radial would be equal to mass times R theta double dot plus 2R dot theta dot. And then we just plug and chug our equations. So I'll do an example, but I'll just scroll this up to do the example and bring it in here if it lets me. Just a sec. So here we have a practice problem, and this is a spatial disorientation trainer. It is programmed to rotate and translate only in the horizontal plane, so we have 2D motion. The pilot's location is defined by these two relationships. So we have R is equal to 8 times 1 minus e to the negative t, and theta is equal to 2 divided by pi times sine pi over 2t. And this question is in imperial units, so we have feet, radians, and seconds respectively. And the question is asking us to determine the radial and transverse components of the force. So we're looking for R theta, we're looking for R force in the radial direction. The weight of the pilot is equal to 175 pounds, and we're looking for the forces at time t equals 3 seconds. Now to start off, this is really important. This is the weight of the pilot is 175 pounds. That's not the same as mass. So if you wanted the mass of the pilot, this would be equal to 175 pounds divided by 32.2 feet per second squared. So for this question, and it's a little bit hard to visualize from this picture, but essentially if you see this part here, this would be sort of a chair that the person would be sitting in. So if you looked from the top down, you would have the pilot kind of sitting in a chair here. The radial direction would be extending out this way. This would be your ER, and your transverse direction would be here. This would be your E theta here. So the question's asking us to determine, and then if I extended this back here, this would be the origin O, this would be the reference, and then this would be the theta. So this would be a top view of the picture, whereas the picture is an isometric view. So now if I draw the free body diagram here, just a sec. Still from the top view, we would have the pilot who's getting tested here. Then we would have the force in the transverse direction, and we'd have the force in the radial direction is equal to the mass in the radial direction and then mass times acceleration in the transverse direction. In this case, we're given equations for R and theta. So when we look at our summation of forces, we have summation of, we have summation of force is in the r direction is equal to m AR. This is equal to m times r double dot minus r theta dot squared. So to figure out how to fill this in this equation, we would just need our r double dot and our theta dot, which just come from our derivatives. Same thing for our summation of forces in the theta direction. We would have m a theta, which is equal to m times r theta double dot equals 2r dot theta dot squared, or theta dot. So to solve this problem, I'm going to move this up. All we have to do is we say r is equal to 8 times 1 minus e to the negative t. The derivative of this is 8 e to the negative t. The derivative of that would be negative 8 e to the negative t. Theta is equal to theta is equal to 2 over pi sine of pi over 2t. So then theta dot is equal to the derivative of that, which would be cos pi over 2t. And then theta double dot would be equal to the derivative of this, which is negative pi over 2 sine of pi over 2t. Now all we have to do is plug these equations into these ones. So you end up with force R is equal to, now we don't have a mass, so we have to do the weight divided by gravity times negative 8 e to the negative t minus 8 times 1 minus e to the negative t cos squared pi over 2t. Our transverse force is equal to W over G 8 times 1 minus e to the negative t times negative pi over 2 sine of pi over 2t minus 16 e to the negative t cos pi over 2t. We plug this in for t equals 3 seconds, and you end up with Fr equals negative 2.165 pounds, and F theta is equal to 64.9 pounds. Even though polar coordinates kind of appear to be more challenging because the equations look trickier, sometimes they're actually easier because you don't have to do any trigonometry, you're not dealing with figuring out what the angles are. So sometimes these problems are actually a little bit more straightforward.